exercising your mind and your body.
Today we're going to be showing you how to get the bronze and the brain.
Our first workout today is going to be jumping to start off with leg day.
To get the best workout, you're going to need to engage that core.
Watch as Mabel and I execute this move with finesse.
On 3, let's get it, ladies. 1, 2, 3. Man, I feel like I burned a lot of energy with that one, Bella.
Well, how much energy? To remember that energy is always conserved once a system is in action, so no energy can be added or lost. This is explained by the law of conservation of energy. This means that once you start jumping, you will have the same amount of energy until you land. The energy does change forms, however. Let's look at this handy-dandy diagram.
Okay. Oh, I get it. So at first I don't have any energy, like in the first picture. When I get ready to jump in the second picture, my energy is converted to work. When I'm in the air, all my energy is in GPE. Right before I hit the ground, or the second to last picture, it goes to KE. When I finally come back to the ground, it changes one last time to thermal heat. But throughout the whole process, I only have as much energy as I started with. Now let's calculate how much energy I used in the first place.
The equation we use for GPE is mgh, where m is mass, g is the gravitational constant of 9.8 meters per second squared, and h is the height. So if Mabel's mass is 60 kilograms and she jumped 47 meters in the air because she never misses leg day, all you have to do is multiply the 3 together. When you do this, you get 27,636 joules of energy expended.
Man, that's a whole 1,000 joules off my goal.
That's okay, you'll get there.
Next up, we're going to show you a modified weightlifting set. Stay tuned, dudettes.
Oh no, I don't have any weights. What can I do?
Well, the easiest solution is totally tubular, man. Just find a furry friend and use him for your shoulder press. At this point, you should be wondering, as a good physics student, what kind of forces are being applied on that talented stranger and the white cotton ball named Humphrey. Let's take this opportunity to explore Newton's third law.
Here we have a force diagram. The forces acting on Mabel are the ones in red. The ones acting on Humphrey are in green. Newton's third law tells us that for every action there is an equal and opposite reaction. So, if Mabel applies 100 newtons of force to lift up the dog applies 100 newtons of force right back at her.
It's also important to notice that the force of Mabel on the dog is equal to the force of the dog on Mabel. This is because that is the third law pair of the system. So even though Humphrey only weighs like 13 pounds, he's applying as much force on me as I am on him?
That's right!
I mean, if you say so. Follow us over there where we're going to show you our next workout. This is a perfect example of inelastic collision.
Mabel's going to sit on the scooter and I'm going to throw this ball at her.
Before we begin with the math, it is important to remember the conservation of momentum equation. It basically states that momentum is always conserved. This is why we can set the two equations we're going to be using equal to each other. The momentum of the two objects beforehand will be equal to the two objects' momentum afterwards.
Once Mabel catches the ball, she moves backwards at 900 meters per second. Let's see how much that ball weighed to push her back at that velocity.
My mass and the scooter's mass combined is 80 kilograms. Since I'm standing still, my velocity is 0. The ball is coming at me at 1,000 meters per second, and after catching it, mine and the ball's final velocity is 900 meters per second. Using the equation, m1 times v plus m2 times v equals m1 plus m2 times v final, we can figure out that the ball's weight is 720 kilograms. Now that we've demonstrated inelastic collision, it's time to move on to our next exercise.
Grab your ropes, ladies!
Woo! We're going to show you how to get an arm workout and create some sick waves, brah. In order to understand waves, there are some key terms you have to know. Amplitude, crest, trough, and point of equilibrium.
The crest is the highest point of a wave, while the trough is the lowest. The point of equilibrium is the line that is level with the starting position of the wave. The amplitude is the distance between a crest or a trough, and equilibrium. But don't forget about wavelengths. That's the distance between two consecutive crests or two consecutive troughs.
The red dots represent troughs. The blue dot is where the crest of the wave is, and the black line is the point of equilibrium. It's time to kick it into high gear, Bella. Let's move to a place with more space.
Time to watch Mabel do some serious sprinting. Time to find out Mabel's acceleration. Here we have a graph showing Mabel's acceleration. As you can see, she accelerated for 4 seconds before reaching her maximum speed of 5 meters per second. To calculate her acceleration, we used the equation A equals delta V over delta T and found she accelerated at 1.25 meters per second squared. After that, she had a constant velocity of 5 meters per second.
Hold on, Bella. We have to explain to them how to find the change in velocity in the first place. So the black dots on the graph represent our x final and x initial. We use x final minus x initial to get the change in velocity. On the graph, when there is a slope, there is acceleration. Up until our x final position, there is an acceleration. Once there is a straight line with no slope, there is no acceleration. All right, another equation bites the dust. Time to move on. It's always important to do a cool down jog after you're sprinting, so let's go do that now.
Wow, you look like CJ Parker out there.
Man, I bet I had a really high velocity and a really fast speed.
I don't think you had a high velocity.
Really? Because I ran like all the way there and back.
But velocity is different from speed.
Is this like scalar and the other one?
Yeah.
Oh, can you explain that to me?
Okay. Basically, scalar gives us one measurement, like how much, but vectors gives us two, like how much and in what direction. Because you ended up running exactly back where you started, your velocity is 0. This is due to the fact that displacement, or change in x, is equal to x final minus x initial. Since your ending and starting places were the same, you had no displacement. When you divide the displacement, which is 0, by the time it took, you'll find that the velocity is 0.
Okay, but even if my velocity was 0, I probably still had a really high speed. Did you even see me out there? Okay, well, I went like 20 meters in about like 2 seconds. So if you plug that into the equation to find speed, which is delta x, or change in distance, over delta t, or the amount of time it took you, you would do 20 meters over 2 seconds, which would be about 10 meters per second. I'm basically in line with the Olympians, all right?
Okay, whatever.
Now Bella is going to push a heavy box across the surface, and we can teach you about friction. As shown by the force diagram, there are 4 forces acting on the box, 2 vertical and 2 horizontal. The y forces, the force of the ground on the box and the force of the earth on the box, are equal. The horizontal forces, or the force of Bella on the box and the force of friction on the box, are also equal to each other because of Newton's third law. Now Bella is going to help us calculate the amount of friction.
To calculate the amount of friction on the box, we first need to find the normal force. We can do this by using the equation normal force equals 9.8 newtons over kilograms times mass. If the box weighs 5 kilograms, then the normal force equals 49 newtons because 9.8 times 5 equals 49. Now that we have the normal force, we can find the force of friction. The equation for the force of friction is force of friction equals mu times the normal force. Since we know that our coefficient of friction is 0.62, we multiply this by a normal force of 49 to get a frictional force of 30.838 newtons. Because of Newton's third law, we know that every action has an equal and opposite reaction. Because the force of friction is negative 30.38 newtons, we know that I applied a positive 30.38 newtons to push the box.
We just finished our workout and we're really hungry, so we're gonna go to Jack in the Box and get some food. See y'all there.
Whew,
Okay, so we found a parking spot at Jack in the Box and we're just pulling in. Oh my god, Bella, look, a puppy!
Where? Okay, so obviously we went from going fast to going not so fast over a certain amount of time. But what equation can we use to calculate this?
So what I think you're trying to explain is momentum. Well, a long, long time ago in high school, not far from here, I was taught that Change in momentum equals mass times change in velocity.
Okay, that makes sense.
So if you went from going 20 meters per second to going 0 meters per second, your change in velocity would be 20 meters per second.
So then I guess you would plug in that along with my 60 kilograms mass into the equation and get that my change in momentum is 1,200 kilograms meters per second.
Sounds good to me. Okay, so that was Bella and Mabel's totally tubular workout for the mind and body. Thanks for watching.